Thank you. Thanks to the organizer, to Gerard, for inviting me here. So this talk is starting with a truly disjunctive talk, because as you may have noticed in the program, I have a title and an abstract, and they are disjunct, in a sense. So essentially, I have to decide, not right now, but at some point, whether to follow the left node, talking about the title, or talking about the abstract. And since we are here in the city of disjunctions, according to a tweet of Tiago Serra, then of course I will go to the disjunctive part. So this talk is about the intersection cuts that of course are due to Egon. You can see some pictures here, and Bill Pullyblank is in the audience, is this guy, and Paolo Tot is the other there, just for you to know. So this became very popular nowadays, so I will talk again on non-convex mixed integer quadratic problems. And essentially our goal was to implement intersection cuts for that problem. And as we are typically aim to produce algorithms that work in practice, then we did an implementation. And this implementation is a design choice, whether you start with a nonlinear solver and build the mixed integer part on top of it. So you implement a branch and bound on top of a QP solver, or the other way around. You start with a very efficient mixed integer linear solver, branch and cut, in our case it was Cplex, and then you customize it through callbacks in order to deal with the non-convexity. There are pros and cons of both approaches, but in this talk I will describe the second one, the second approach, which is quite common. I mean, we saw in these 2 days, several times this kind of approach. So this is the mixed integer quadratic problem that I want to solve. So you have a standard definition, but actually for solving this as a linear program, then we used the trick with, by the way, this is joint work with Michele Monaci from University of Bologna. So we used the trick of putting all the nonlinearity, the quadratic terms, in additional variables. So essentially, we have a mixed integer problem plus bilinear equations that are the source of the problem, of the difficulty. So I will skip everything which is quite standard in our implementation, McCormick, branching, spatial branching. Actually, there is a paper here on this subject already published online by Ijor, and this material goes back to a couple of years ago when we started. So, I mean, I'm not going to describe all the important parts which are rather standard, but again, I will go to this intersection cut stuff, of course, in honor of Egan. So this is a very basic way of describing the intersection cuts. You know, Gerard also gave a nice presentation about it. During the branch and cut, you face a situation in which you have a point. This is not necessarily a fractional point. Here, the point can be integer, but does not satisfy the bilinear equation. So this is bilinear infeasible, either because it is fractional or more often because it is integer, but does not satisfy the quadratic part of the constraints. And you have a bunch of feasible solutions. In this case, it's a discrete set, it doesn't matter. Now, in order to cut this point, so to produce an inequality that separates X star from this point, what you need is essentially a cone pointing at X star that contains all the truly feasible solutions, and a convex set, actually polyhedron in our case, with the property that this polyhedron contains X star in the interior and no other feasible point in the interior. So feasible point can be part of this closed set, convex set, but only on the border, on the frontier. Now, once you have this stuff, then by using some geometrical argument, you can easily, so to say, derive a linear cut that makes the job, that separates the two. Of course, you have to decide that these two actors in this setting. One is the cone, and the other is the set. So the cone you typically take from the linear programming relaxation, because essentially in a branch and cut, you get from free the optimal solution, so the optimal basis associated to this X star, And this optimal basis produces implicitly a corner polyhedron that acts as the cut, the cone that you need. So this is not necessarily the best possible choice, but let's take this for granted. So we go and take the green cone as a cone associated to the LP relaxation. So it is hidden in the inverse of the basis of the current optimal basis, or if you want to use an old terminology, in the optimal tableau that you have at the node. Now, the second part is taking these bilinear free sets, so the lattice free sets in the context of mixed integer. Here, they are not lattice free, but they are bilinear free sets, so to say. The idea is that the larger the set, the better, of course, because the cut has more room to move. You will produce improved cuts. And then the way you can do this is, of course, very much dependent on how much research effort you want to spend on this. Essentially, the idea is that whenever you have a point x star that you will be able to cut by using a branching disjunction, then using the branching disjunction, you can implicitly, easily derive the set. So at any point when you have this fractional, this solution x star, which is infeasible, if you are able to branch on that condition, then on the other hand, you are able to produce an intersection cut using the same disjunction. The idea is very simple. You see, if you have this kind of disjunction, so essentially you imagine you could branch on this disjunction to cut x star, then if you just revert the inequalities that are the branching condition, that you get a set. And by definition, this set contains x star because you are assuming that you are able to cut x star in the branching. So x star is in the interior of this set S, and no feasible solution is inside this set. So again, branching or generating an intersection cut is just a computational choice. If you branch, then those inequalities are completely fulfilled in the descendant nodes, in the child nodes. But of course, you are doubling or multiplying the number of problems that you have to solve. So you have the classical explosion in the branching tree. On the other hand, if you take a single cut before branch, without branching, then this cut, in a sense, is a surrogate, so contains part of this information. But of course, you cannot guarantee that this information is really fulfilled by a single cut in the problem that you are solving. And deciding whether to branch or to generate this kind of cuts is, of course, very, very important. And of course, these cuts tend to have some numerical problems. So you tend to use these cuts only when you have a proof that this cut, or you have a guess that these cuts are really effective. Now, I'm not talking too much about how we decided the branching disjunctions that produce the set S. Essentially, in this context, you typically branch, apply what is called spatial branching. It's a strange kind of branching because the solution x star is not cut by the branching condition, but the branching condition allows the generation of McCormick inequalities that are tighter, and the McCormick inequalities are actually doing the job, so they are able to cut the fractional solution. So essentially, if I branch on a disjunction like this, which is called a spatial disjunction, then I'm implicitly introducing a certain McCormick inequality in the left node, a certain McCormick inequality in the right node, and these are the actual disjunctions that define the branching, and if you revert them, these are the conditions that define the bilevel free polyhedron. Now it comes to the implementation. Now we did a similar approach for solving bi-level problems years ago, together with Ivana Lubich and Markus Sinnel, and from the University of Vienna at the time, and Michele Monaci, of course, who is a co-author also of this paper. And in that setting, intersection cuts were very powerful. I mean, we were very surprised that they were so powerful. I know that Gerard told Egon that we had this application, very powerful application of intersection cuts. So maybe today I would have talked about that implementation, that very nice computational results. But this is a more recent work. So we use essentially the same machinery. And the key point of our implementation is the stuff that I'm going to describe on this slide, which is a slightly different way of generating the intersection cuts. The idea is that we would like to have a way to generate the intersection cuts that are numerically reliable. Francois Margot is no longer coming to our meetings, but years ago, he was always asking, are you sure that your inequalities are valid? And with intersection cuts is a matter of tolerances. Because you have to follow the ray, and you have to compute a certain number along that ray. But if that ray does not point in the right direction because of numerical problems, then it is not very clear how you have to compute that number. So you have to use tolerances and so on. So it's a kind of a mess to implement this. So when I had to personally implement this, I decided to take a different view of this intersection cut generation, and which actually goes back to Glover. Also, in my case, Glover plays an important role, in which essentially you, instead of taking the description in terms of intersection cuts, you have the description in terms of disjunctive cuts. They are very well known. They are equivalent. This is very well known, but I want to describe a little bit the machinery that you have to apply to solve in a numerically safe way the cut generation function. So let me change notation because this is going to be completely general. So you suppose you have a linear program, and in a standard form, this is important, you want to use only equations, and you have no bounds on the variables. When you implement this stuff in Cplex, then of course there is a tricky way. You have to convert everything to this theory. So again, be careful because we are talking about equations and non-negativity variables without explicit bounding condition on the variable. Now I assume to have this set given on input. These are the condition, the branching conditions reversed in a sense, and this is the input set. So I have a k-way branching in a sense. So I have k disjunctions in the set of k inequality, k facets of this polyhedron. And of course, the disjunction which is implicitly there is the one on the slide. Now, how can I produce a valid inequality for all the child nodes? So this is the problem. I want to produce a cut which is valid for all the descendant nodes of this potential, if I would branch, potential descendant node. So again, if I take an inequality like the one on the top, every inequality in the disjunction is valid, but not overall. It's only valid for the sun node that defines the set. So the idea that goes back, I think, to Jarrow's law is that I can essentially manipulate these inequalities so as to get a single inequality which is valid for all the sets, for all the branching suns, for all the polyhedron whose union you are going to describe. The idea is very simple. I want to weaken this inequality, each of these inequality, so that in the end they become identical. So how can I do that? Very simple. For each coefficient in the left-hand side, for each inequality, I take the maximum. So I take the first variable. This variable has different coefficients in the k disjunctions. I take the maximum, and I repeat this on the left-hand side. And for the right-hand side, I do the other way around. I take the minimum right-hand side. Now, of course, this is a weakening because our variables are non-negative. This is a weakening of each single variable, each single inequality. But the inequality in the end are the same. So a single inequality now is valid for everything. Now, if you do this, you, of course, obtain a valid inequality. But this inequality is so poor that it's no longer acting as a cut. It's not guaranteed that you cut x star or psi star in my notation, which is my idea. So the point is that you want to manipulate the inequalities in such a way that after applying this Jarrow's law procedure, taking the maximum coefficients, blah, 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 then the inequality is still violated by x star. In the beginning, they are violated by x star. So you can essentially you can have two approaches. Let me put this in this way. You can use Farkas lemma and say, instead of using the single inequality in the given form, I can consider a linear combination of these inequalities with the other equations, actually, that define the polyhedron. So essentially, I have Farkas multipliers for each subproblem, or dual variables, if you prefer. And I have a complete freedom of deciding these multipliers. Then you combine using these multipliers and apply the Zerov's law approach, which are the best possible multipliers that I can decide for each subproblem in order to maximize the violation with some normalization condition. But this is a linear program, and this is actually the cut generation LP. So if you want to produce the best possible aggregation of these inequalities with the original set of equations to get the most violated cut, valid cut, using this procedure, you have a cut generation LP. Very nice, this is disjunctive programming, but can be time-consuming. The other way is that you say, okay, but I have some information in my tableau, in my optimal basis. Why I don't use this information to get in an easy way the intersection cut? Now, the easy way is very simple. You know linear programming. You know that the objective function at the end of when you have a basis can be put in the so-called reduced form. And in this reduced form, all the cost of the basic variables are 0. Remember that x star is a vertex, so since it is associated with a basis, only the basic variables are positive. All the non-basic variables are 0. So the trick here is that instead of taking the inequalities in the original form, you don't see the point, but in the top there, then I manipulate the inequality and put the reduced form so that all coefficients of the basic variables are 0 in all of them. At that point, you can easily see that the right-hand side must be positive because this inequality is violated by the fractional point. The left-hand side is 0 for the optimal basis solution, again, because of complementarity. The coefficient is 0 when x is positive and the other way around. So if this is violated, the right-hand side must be strictly positive. And then you just divide everything like this in order to get the same right-hand side. Now, if you apply now the Zerov's law approach, what you get? For the basic variables, all the coefficients are the same, are 0. So the basic variables are still at coefficient 0. The non-basic variable can have terrible coefficients, but who cares? Because so far, xi star is 0 for them. So in the first approximation, they don't count in the left-hand side. And the right-hand side are all equal to 1, so you don't lose anything when you take the minimum. So this approach is essentially the way that you can use to derive something that it turns out to be the intersection cut. I have to say a little generalization of the intersection cut, which is essentially like this. You go into all the inequalities, you compute the reduced form of the inequality using the standard linear programming formula. In linear programming, it should be C transpose B to the B to the minus 1. This is not C, but it is a single inequality. After this step, you just compute the maximum of the coefficients, and the right-hand side is 1. And this inequality is guaranteed to be violated by 1. Why I claim that this is safer than the other way around? Suppose the B to the minus 1 is not perfectly accurate. So you have some numerical error here. Okay, so these multipliers are not perfect. So what is the difficulty there? Since I use this multiplier to recompute the coefficient, the validity of the inequality is not affected by the numerical error. So the inequality is valid because no matter the coefficients that I decide to use, when I make the combination, I combine this with the original inequality equations in the original system, which is supposed to be very precise representation. And then what can happen is that the coefficient of a basic variables that in theory should be 0 is not precisely 0. It's 0 point something. So this means that the violation is not exactly 1, but it is a little bit less than expected. Of course, if you have a lot of these errors, the inequality is no longer violated and you have to skip it. But anyway, this will produce you 100%, well, let's say, very safe intersection cuts without too much numerical issues. Of course, if you have a very bad data, numerically speaking, the inequality is not the one that you would like to do. I have to say that this is so general that I implemented a function that you give a basis point, a pointer to simplex object, and it does for any problem. Applies this. So essentially the same that I implemented for by level, now I'm using for free as a function for this problem. Just to say here that, of course, this inequality is not guaranteed to be strong. You could maybe apply monoidal strengthening here, so apply Ballas and Gerosov to improve this. There is a nice paper by Ballas and Qualizza in which they show how to do that. You should try to reduce, before applying this stuff, to improve the disjunction on which you branch using some properties. So this implementation is very basic. I'm not claiming this is very good. For mixed integer programming, you will get not even the GMI inequality here if you branch on the split disjunction and not on the row that generates the Gomori cut. But anyway, this is a way that you can implement easily. So what we did in just a couple of minutes, we did our clever implementation, going to simplex through callbacks. And actually, in our implementation, we trust simplex engineers that are all previous students, friends. So they did a very good job. So our idea is that we want to modify the code as little as possible. So whenever simplex knows how to generate a cut by mixed integer, I will let it generate the cut. Whenever simplex knows how to branch, we say, okay, go ahead. Whenever simplex say, for me, this point is perfect, then we enter in the callback and either take the branching condition that we like, the spatial branching, or we try to generate this. No, we have no specific heuristics, only no specific quadratic problem heuristic. So what are these computational results? We made a comparison of 3 versions. Skip was a benchmark for us. The basic version is without intersection cut, and with intersection cut is the other implementation that we get. Technical details here, we used about 700 instances available in the MIPLib. I'm not going to present the tables, but more a performance profile. If you compare the 3 methods, you see that, strange enough, the simpler seems to be the better. So not using intersection cuts, on average, on this large test set, is the best thing to do. And we are, let's say, comparable with Skip, even if our implementation is rather simple. But of course, we build on top of the giants engineers at a commercial solver. Sorry, Michael. Commercial solver in general, not simple. And the intersection cuts do not work very well. We did also some other experiments removing some instances. This is a little bit unfair because we remove small instances that apparently are more difficult for us than for simplex. So this is not a fair comparison. But still, you see that the intersection cuts can play a role in some problems, but are not on average very fundamental for solving a problem. This could be also expected because adding cuts is not always the best choice. But for some problems, of course, some structure of problems, intersection cuts can make a huge difference. And these are some examples in which with intersection cut, you go much better. So the performance is much improved. So again, this is like a Gomori. You don't apply Gomori cuts every time in a very aggressive way. When we generate intersection cut, we do at every node for every integer solution that we get. So we don't have a clever way to control the computing time. Anyway, that is the end of my talk, and the paper is available as usual in my web page. Also, these slides are there. And now you could also find it on online with the EJOR, European Journal of Operation Research, in an online version. Thank you. just to say, I'm the culprit, one who moved the Egon photos from there to there, because I mean, this looks like Oswa in a sense. The color is the same, and we all remember Egon sitting more or less in that position during the talk. So I wanted to have him in front. So it looks more familiar to me. Okay, thank you.